So let's continue on into section 3.2. So the next thing we want to talk about is residuals. Okay, the model isn't perfect. A lot of times, unless we have a data set that makes a straight line, we're going to have something that's going to be off. We're going to have some little bits of error here and there. In most cases, no line that passes exactly through all points in a scatter plot, okay, unless the line is perfect. A good regression line makes vertical distances of the points from the line as small as possible. We're going to see something of that. I'm going to try and show you some dynamic models of that too. So we have a definition here. We have a residual. A residual is the difference between an observed value of the response variable and the value predicted by the regression line. Okay. And we'll talk about this again when we have a picture in front of us. When we're finding a residual, we're always looking at the actual value minus the predicted value. And how do we remember that order? Well, a nice little thing that we have is actual minus predicted, AP, just like we have our AP stats here, right? Y minus Y hat, or Y minus predicted Y. Think AP, or actual predicted. So if we go back to that graph where we had the price in dollars and the miles driven, notice how our line cuts through all those points and hits almost no lines perfectly. That distance, that horizontal distance that we have from the actual to the predicted is called the residual. So here, if I look at this data point here, this was the actual down to the predicted. This distance here, remember in mathematics, we measure distance as a straight line. Okay? It is predicted here, and we can have residuals here above this actual minus predicted. So that's going to be a higher number minus a lower, so that's going to be a positive value. And down here, take a look at this. This data point was actually a lot lower than what was predicted. So if we did actual, a smaller value minus predicted, it would be negative. And I'll show you a little bit of that in just a minute here. So notice that we have positive residuals. Those are ones above the regression line. So actual minus predicted will have a big value here minus the predicted value, big minus small. That's going to give us a positive number. Negative residuals are below the regression line. We have an actual value that is small and the predicted value is bigger, right? So we have a small number minus a bigger number, so it's negative. That would be a negative residual. So let's find and interpret our residuals here. Here is our least squared regression line again. The predicted amount of soda is equal to 2.48.2.63 tapping time. And remember that that is our slope, 2.63, change in y over change of x, 2.63 over 1. So on average, we would predict that for every 1 unit of x, for every 1 second, we predict it would go up on average 2.63 milliliters of soda. So let's calculate and interpret the residual for a can that was tapped for 12 seconds and had 290 milliliters of soda remaining. So we're looking at this point up here in green. Notice this has 290. That's a lot higher than what we predicted here with our regression line. So what happens, that becomes a positive residual. We have the actual minus the predicted. So the actual was 290, and the predicted takes our equation here and puts in 12 for the tapping time. The predicted y was 280. So our actual minus the predicted was about 9.84, and that distance is our residual, and that is above the line. That's a positive residual. Now, what about for number 2? When it said that it was tapped for 4 seconds and it was 250, that's down here. That's less than what was predicted. So what we see is it's going to be below the regression line and it's going to have a negative residual. We take our predicted, again, here's our least regression line, and we put in 4 for 4 seconds, and our predicted was 259.12. Now our actual was 250. Our line was higher than that. It was higher than what we had. We predicted for it to be higher than what it was. So actual minus the predicted, the residual was negative 9.12 milliliters. So we can see we can have positive residuals that often fall above the regression line and negative residuals that fall below the regression line. So we have a least squared regression line. The different regression lines produce different residuals. The regression line, we want one that minimizes the sum of the squared residuals. Okay. So kind of the idea here of a regression line, we have what's called a least squared regression line. And we'll show you a picture over here, and then I'll show you kind of a more dynamic model that moves around. So what we do here is we take all of these points that we have here, and we draw the residuals. A quick vertical line from the actual point to what's predicted. And then what we do is we square those. This is a lot like standard deviation, where we have the median, and then we have points below the median and points above the median. And if we were to take those distances and add them together, we would have distances that were less than the median and above the median, they would cancel out. We can't have those cancel out. So in standard deviation, we square those before we combine them. So what we're doing is we are taking these, sorry for that pop-up, we're taking these residuals and we're squaring them and we're putting them together. And the smallest amount of squares that we have are the best. So let's pop over to a dynamic model here in Fathom. This is a model of carbs and fat, and we're going to see that with a relationship in a little bit about the relationship between carbs and fat in McDonald's sandwiches. So here I have all of these here, and I have some points that are above. Those would be positive residuals and some that are below. This line coming through is my regression line. Okay. So what I'm going to do is I'm going to ask it to put the line of best fit or the least squared regression line for me. It's there. What I want to do is I want to make my residuals come in. So I'm going to have that here. So what happened is the residuals are in here and we have the squares. Now, if we take a look, this one here, this is pretty much real close to being just as far above as this one is to being far below. But if we didn't take a distance and square those, these would cancel each other out. As the line moves from our different residuals here, these squares get bigger and smaller. Okay. If I take a point, so let's take this point right here. If I were to move this point, notice that the closer it goes to the line, that it has a smaller distance away. In fact, if it's on the line, it has no residual. Okay. If I were to take a point here and I move it further away, that's more of a squared distance. Notice down here, what's moving is called the sum of squares. The residual model works really hard to minimize the sum of squares. Okay. So what happens is when that line cuts through, the line's cutting through and saying, okay, this is the smallest amount of residuals that I can have. And we notice that if lines are cut closer together, then they're going to have smaller residuals. If I try to take these points and get them closer to what we have here, right? If they're closer to making a straight line, then the residuals are going to be really small. Okay? But if I go back to original data and I see that those data points here are starting to get further and further away from what we had, or back to the original data, then we can have that line. So the line tries its very best to model that. And again, if we show our squares here, we can see that points that are far away have a lot larger residual. And again, we square those residuals, so we add them all up. It's a collection of what we have. This sum of squares right here, right? We're trying to minimize it. So we minimize the area that we have, and we have some great stats moves and pre-calc and calculus moves to minimize an area under a curve or to minimize area. So that's why the regression line is very often called the least squared regression line, because we're looking for the smallest value to square our residuals. So here's something we're going to practice. We're going to do this. We're going to say, fat and carbs. The data below is for 9 McDonald's beef sandwiches, and you can find this example in packet page number 8. So we have a data set of these 9 sandwiches, and we have a relationship between their carbs and their fat, okay? And that was back here. That's what I have in my original data set here, so we can kind of see what that scatter plot looks like. And then we're going to work there to see what we can get. Okay. So that's going to be our scatter plot here, and we're going to work on putting this with our calculator. So once we do that, we're going to enter the data into the list. We're going to use the calculator to get our least squared regression line. We're going to write out the least squared regression in context to remember that it's not about y's and x's. We're going to look towards kind of old school, do with the correlation coefficient, and what 2 things can we tell you about the relationship. Some rehashing of 3.1. We're interpret the slope in y-intercepting context. So that's what's new about 3.2. And we're going to calculate and interpret the residual for the Big Mac. So the first thing I'm going to do is I'm going to help you get this going in our calculator, and then we'll switch over to our answers and see how you did. So make sure that you're practicing this yourself and trying to get your ideas on your packet first, and maybe pausing. I'll remind you just a minute where to pause. Before you go and look at the answers. Try it before the answers, okay? Allow yourself to make your mistakes instead of just looking at the answers and copying from there. So I'm gonna go to Stat, and I'm gonna go to Edit, and I've already put my points in. Remember that we're just putting our X's in. This is gonna be our carbs, and our Y is gonna be our fat. So when we get the slope, the change in Y over change of X is gonna be the average change of grams of fat over our average, over our change in carbs. So what I want to do here is there's a couple of things I can do to get to this data. Again, remember I went to Stat. So if I wanted to plot it, I would go to Second Stat Plot. And I'm going to turn that plot on. And I can see that this is going to be a scatter plot. And I have list 1 and list 2. So I'm going to zoom. I'm going to zoom to my stats. I'm going to take a look at that. Plot right here. So here's what we have. Remember that we can hit trace and look at different things here. So as I go right, I can look here and see, okay, this is the plot. This is the 40, 26. So this is the sandwich with 40 carbs and 26 grams of fat. So that's something we can do that's really nice is we can make that scatter plot. Okay, so we can copy that. We'd want to make sure that we're labeling our axes, both X and Y. So there's a nice way we can do it. If you're drawing out your scatter plot, that's okay too. So the next thing we're going to do is we want to make a least squared regression line. So we're going back into Stat, but now we're going to go to Calculate. Remember that the form that we're talking about in our book is down here in 8. This is the line of regression, or regression line, A plus B of X. So I'm going to hit Enter there. It's going to ask me, where did I put in my X? Or where did I put my X values? I put those into list 1. And if this is cleared out, you can't remember, that's just above the 1. Right here in blue. So I'm going to go second 1. That's going to be my list 1. Now I'm going to go to list 2. Frequency should be cleared out. Store regression equation can be cleared out for now. And I'm going to hit calculate. So notice here in my calculate, I get a lot of great things. And we kind of saw this before too. This was kind of the way that we snuck to see what R and R squared was. So here is my equation. Y is equal to A plus BX. A is the negative 40.2. And B is the 1.71. So my predicted Y, it would be my predicted Y, or my predicted fat, is equal to negative 40.2 plus 1.71 X, or what we would have for the fat here. So let's go take a look at the work on the next page. Pause if you haven't yet. Try some of these yourself, thinking about how you would do this in context. And now we're going to take a look. Quick pause in case you're going to have to run back to your screen here to do it. All right, we're going to the next one now. Remember real quick, if you're not seeing the R and the R squared, that we should go through these steps to turn it. We talked about it in 3.1. You don't have to do this often unless your calculator is reset. But just a quick reminder that if you don't see the R and the R squared, you have to turn your diagnostics on. And this is the screenshot from 3.1, how to do that. All right, so here's our key. We can see that carbs was our explanatory value. and fat was a response variable. So we write it out in the least squared regression line. Y hat, or predicted Y, is 40.2, 1.71x. Let's put that in context. So remember that Y is fat, so that's her predicted fat, is equal to 40.2 plus 1.71 grams of carbs, okay? Now from 3.1, what does R mean? We can see R is 0.743. What's the correlation coefficient? What are two things that we know? Well, we know that we can see that it's like a positive correlation, and so we can see it's a positive direction. That means as carbs increase, the fat tends to also increase. And we can also see from the R being close to 1 that it's a strong linear correlation. So that's really nice. So let's interpret the slope and y-intercept here. I kind of put y over x, so I have 1.71 over 1. So that's 1.71 grams of fat over 1 gram of carb. So remember that this is a prediction and it's on average. So when you interpret slope, you need to do that. You need to put on average, because that's what slope means. And to tell them that we're working on this model, we need to have a prediction there. So what I have is for each additional 1 gram of carb, the fat amount is predicted to go up to or increase on average of 1.71 grams. So important here to have the predicted and the on average. The predicted is telling us that we're using a model. The on average tells us that we know what slope means. What about the y-intercept? When the carbs are 0 grams, the amount of fat is predicted to be negative 40.2 grams. Now we know that's impossible, and we might have to interpret sometimes in context that when you have 0 carbs, there's actually a negative amount of fat. Sometimes I'll ask you to interpret that in context, but that's what we have here. That's what the model tells us. Calculate and interpret the residual for a Big Mac. That's the one that has 45 grams of carbs and 29 grams of fat. So mark it on the scatter plot. So if we look on the scatter plot here, we can see that we have an actual, it's 29, but it was predicted by our model, and we put the prediction right in here, to have 36.75 grams of fat. So we do a residual, actual minus predicted, AP. The actual was 29, and the predicted was 36.75. So that's about negative 7.75 grams. So what we say is that Big Mac actually has 7.75 grams of fat less than what we would predict by our model. Okay? So that's a really nice sum up of kind of using our skills from 3.1 and 3.2 back here on our page, packet number 8. So this would be a great time to take a break and do homework number 4. Just kind of doing baby steps here. Now, it looks like we're not doing too much between it, but it's really the precision that we need in these interpretations. That's really where the points lie. That's really what we're looking at. So remember, we want to calculate and interpret the residuals in context. We want to explain the concept of least squares. We use technology to find the least squared regression line, and we found slope and intercept of least squared regression line from the means and standard deviations of x and y and their correlation. That last one, we don't have as much. Kind of finding it by hand. That's something that is almost never on the test, and we're super predicting that it's not going to be here on ours either way. We'll look at it a little bit and kind of talk to you about how that works, but it's not something that we have to worry about at this time. So we're going to take a pause in just a second, and then we're going to move on to the next section. If you're stopping here, that's great. Just pause your video, kind of write down somewhere to where that minute was so you can come back and look at it. I'm on a roll, so I'm going to keep going.